So the last thing we're going to do with accumulation functions is what are called initial value problems. These I think are pretty interesting. So I have an example of what a very simple initial value problem looks like down here. So you can take a second to read it. And these problems are interesting to me because it always seems like you don't have enough information to answer the question, but actually you do. So it says g is an antiderivative of f, and we have the graph of f. So I'm just going to make this note now that the graph of f is also the same as g prime, right? Because g is an antiderivative of f, that means the derivative of g is f. So this is the graph of a derivative, and we're trying to get back to the original function. So I'm trying to figure out what the value is at g of 9. And all we know is that g of 6 is 1. So this seems challenging, and again, like you don't have enough information to tackle it. I want to pose an even simpler version of this problem to help you kind of develop the logic behind these, and then we'll return to this example. Also an initial value problem. Suppose you're 3 blocks from home, 20 minutes into your walk, and then you continue to walk. Then you walk 4 blocks further every 20 minutes. How far are you from home after 120 minutes? Okay, so you guys are all smart enough to figure this one out. I want to divide this up into 2 pieces is how I want to tackle this, because it's going to relate to how we tackle this problem down here. So we are going to start with 3 blocks, 20 minutes into your walk. So 3 blocks from home plus, so this is my first 20 minutes. I need to account for the remaining 100 minutes. So I know the distance I traveled in the first 20 minutes. I want to know how far I am 120 minutes into my walk, so I have 100 more minutes to account for. So 4 blocks further every 20 minutes. This is all just arithmetic, right? So 100 divided by 20 means there's 5 20-minute periods in that walk. So I'm going to do 5 times 4, right? So 5 periods, this is a time, and this is the change per time. So this is like blocks per time. So the result obviously is 23 blocks from home. Pretty far, 23 blocks. Okay, so think about how we just did this, right? We took this initial value, the initial value, so here's our initial value in our calculus problem, and then we added up the change, right? So we added up the change over the remaining period. Pretty smart, right? And that's exactly what we're going to do down here. So what I want to do on the graph is I want to highlight my x's that I'm working with. So I have g of 6, g of 9. Okay, so I'm only worried about this period from 6 to 9. Okay, so what I want to do is I want to take my initial value. So I know that at 6 minutes, or whatever we're talking about here, I'm starting with 1 plus the total change from 6 to 9. And the total change, that's an integral, right? So that would be the integral, the area under this curve. I'm going to write it out formally so you can see it. So g of 6 plus the integral from 6 to 9 of f of t dt, or f of x dx, doesn't really matter in this case. So notice that is an area. This is super cool, right? So this would be just 3 times 5. So we do 1 plus base times height. 3 times 5 is 15. And 16 is my result. So we say g of 9. Well, g of 9 is g of 6, where I've given that I started at, plus the change between 6 and 9. So g of 9 is going to be 16. Look at how similar this looks to this, right? It's the same problem. So the change is represented by the integral, and the initial value is given to us. That's why these are called initial value problems. So this allows us to figure out, for example, the distance we travel at a certain time, even if we don't know the distance function, which is pretty cool. We're going to move on to a slightly harder example of one of these, so take a second, make sure you understand how I solved this one before you move on. Make sure you have this captured in your notes as well. So this example here is exactly the same as the previous one with one little twist. But the twist we're adding is something you've seen in previous lessons and already are good at. So this will go well. Let's just double check what we got here. We have f prime is given to us, and we're talking about f, right? So again, this is the graph of the derivative of the function that we're interested in. So that tells me that this is an initial value problem. So I'm going to set it up the same as the last one. Notice it's a little bit different from the last one because this one, it says I have the graph of f, but then it tells us that f is an antiderivative of g. So really we have the same relationship between our two functions going on. So I'm going to set it up the same way. So I'm given f of 6. So the way I'm going to tackle this is I'm going to say f of x equals f of 6, because that's all I got, plus the integral from 6, because again that's all I got, to x of f prime of x dx. Okay, so we didn't really talk about this, the setup, this kind of more general setup before, but this is just an accumulation function that you know how to tackle, right? So I kind of skipped this step in the last one by plugging in that 9 right away. Here I'm starting a little bit more generally, and then I'm going to substitute things in. Either way starting out is fine. If you want to write this as the general form and then plug things in, that's fine. Or if you want to start with what I'm about to write now, so 4, f of 6 is 4, plus the integral from 6 to negative 3 of f prime of x dx. Okay. So let's mark out our x values on our graph. So here's the region we're interested in. And here's the change. What we have here is an integral with the greater bound on the bottom. So we're going to rewrite it first. Minus the integral from negative 3 to 6 of f prime of x dx. Okay. So you can think of it as we're starting here and we're moving backwards. So we're moving to the left, so we're subtracting. Or you can tackle it, think of it as like just reversing the bounds and switching the signs like we've always done. Now I just have to figure out what that integral is. I'm going to use my area formulas in this case. So I have a 3 by 2 triangle. 3 times 2 times 1/2 is 3, and that's a negative, right? And then I have, let's see, a 6 by 2 triangle. So 6 times 2 times 1/2 is an area of 6 for this triangle. So I'm negative 3 plus 6 is the value of this integral, so I'm going to say 4 minus, and I'm going to do parentheses, negative 3 plus 6. So that keeps the minus here. This gives me 4 minus 3, which gives me 1 as my result. Okay, so that's the only complication that we can add. Is just you have to pay attention to these bounds. Okay, so what is given to you, that x value always goes on the bottom of your integral when you're starting out, and then you may rewrite. Okay, so in our first example, we were given, well, also 6. We put that on the bottom. We did from 6 to 9 because 9 is what we're trying to find. We did the same thing here. We did from 6 to negative 3 because negative 3 is what we're trying to find. And then we noticed that our integral needed to be rewritten, so we did that and made it negative. And make sure you have this captured in your notes. You're going to crush out these problems, no problem, I think.